Okay, so last class we did a kind of a big overview of the immune system, and then we also dove specifically into the innate immune system, which kind of has that same exact response no matter what the invader is. And now we'll dive into the details of the adaptive immune system, which is the other arm of it. Okay, so let's go ahead and talk about this one as kind of a review to what we've talked about, this term APCs, antigen presenting cells. Okay, go ahead and chat with your team about this and decide which of these are the ones that act as APCs. All right, go ahead and put those answers in, hit the send button. All right, make sure to hit send. All right, I think there's some more of you that need to hit send still. While I'm waiting for you to do that, I did double check what I was supposed to remind you about with lab. The other piece of your clothing was that you have to wear shirts with sleeves, and that specifically just says short or long, no tank tops. Okay, so that's the other one. Okay, so long pants and some kind of sleeves, meaning just no tank tops. Okay, all right. Okay, so we got 42. All right, so it looks like most people are saying A, and then we got about 2/3 of you saying D, maybe another 40% saying C. So A is definitely one of them. Macrophages definitely act as APCs, and then dendritic cells is the other primary one. Okay, some of you said C. Now, these antigen presenting cells present the antigen to T cells. So that's where it could be kind of confusing, but the T cells aren't antigen presenting cells themselves. They're the ones that get the antigen presented to them once that gets back to the lymph node. Okay, so those are the two primary ones. Okay, so let's kind of talk about the overall process here with the adaptive system. Okay, so the whole adaptive system is activated by these antigen presenting cells. And again, the ones we just talked about, those macrophages and dendritic cells. Okay, they get a hold of the antigen. Okay, let's say it's a bacteria. They engulf that bacteria, they break it down, they save little pieces of it, and then they express those little pieces of those cells on the outside of their cells. Okay, so they present the antigen itself and their MHC2 protein. Remember, that was kind of like the law enforcement ID. The MHC1s were the ones that the immune system is going around checking to make sure cells have. And then the MHC2 is the one that's only present in the cells of the immune system. Okay, so they're going to present that antigen along with the MHC2. Okay, and then it activates both arms of the adaptive system. The first arm of the adaptive system is called the cell-mediated response, and that is carried out by T cells. And then the other arm of the adaptive system is the humoral response, which is activated by T cells, but carried out by B cells. So those two that uncovered on the bottom for you guys in the back there, T cells, and then below that, B cells. Okay, so both of these are all, both these arms of the adaptive system are activated by T cells, but cell mediated is carried out by T cells. Humoral is carried out by B cells. Okay. So we're going to start with talking about the cell-mediated portion of this. Okay, so this is like the first phase of the adaptive response. Okay, it's going to start with that APC presenting an antigen to a helper T cell. So the helper T cell is kind of the key connecting point between the innate immune system and the adaptive immune system. Okay, a helper T cell has a CD4 protein. Okay, so the CD4 protein that comes off of that helper T cell is going to bind to that MHC2 on the APC, which is like that law enforcement ID. Okay, so yeah, so that CD4 protein is going to bind to that. It's kind of like the checking. All right, is this cell legit to be showing me something that is a foreign invader? Kind of a checkpoint there. Okay, and the function there, yeah, to make sure the APC is an immune cell. Also, this kind of amplifies the response, gets those two cells connected to each other clearly. Okay. And then there's one more connection that happens. The other connection is the T cell receptor binds to the antigen. Okay, so it's just called a T cell receptor. That's a very general name, but that's what it's called. T cell receptor binds to the antigen that the APC is sticking off of its membrane. Okay, so one connection is CD4 protein with MHC2 of that antigen presenting cell, and then the other connection is the T cell receptor with the antigen. Those are the two connections that need to happen to activate the adaptive immune system. Okay, so now this like activation happens. It's kind of like a lock and a key type situation. Then everything activates. Okay, so from there, both cells are going to release interleukins and other cytokines. Okay, the function of this is to activate both of those cells right there. Okay, both the ones that are there together, and real specifically activate that helper T cell to then start proliferating. Okay, when that helper T cell starts proliferating, it divides, makes a bunch more T cells. Okay, some of those T cells are going to turn into the type that actually goes out and carries out the action of attacking the invader. Those are called the cytotoxic T cells. Some of those are going to turn into memory T cells. So we're able to remember that exact antigen and attack it again next time. Yeah, so that whole thing says to activate both cells. That's one part. The other part is to stimulate T cell proliferation and differentiation. So proliferation just means we're making a bunch more T cells. Differentiation means we're differentiating into different types of T cells. So some of those cytotoxic ones, the ones that go out and attack the prey, some of those memory T cells, some of those regulatory T cells, all those types of T cells we talked about last time. Okay. And then this also, the release of these chemicals, cytokines and interleukins also activate other T cells that are in the area to start getting ready to attack this same exact antigen. Okay, so this is kind of all the activation part of the adaptive immune system. So questions on this so far? Okay, so take a sec with the people on your team and turn around if you're in the front, work with the people on your team here. You are going to fill in the letters there are labeling just of structures, okay? And then the numbers are the steps in this activation process, okay? And then you can go ahead and send in the answer to that question there on your clicker on the top, okay? Go ahead.
Wait. And then I said, is the release,
All right, so you're sending in the answer to that there. Which letter is pointing to the helper T cell? All right, go ahead and send that in if you haven't. I'll leave it open, give you a chance to do it. But let's go ahead and come back together and we can work through all of this here together. All right, so we have our APC here, probably a dendritic cell. And then we have our helper T cell, okay? So, and then we see the four components that make those two separate connections between the cells, okay? So A is gonna be that CD4 protein, okay? This comes off of the helper T cell. And you can see it kind of binds to the receptor on the APC, okay? And then B is going to be the MHC2 protein. That's the one that it binds to, coming off of the dendritic cell there. Okay, so that's one connection, right? CD4 protein with MHC2. Okay, and then we go to just labeling that cell. So C is the APC, it's a dendritic cell. D is going to be the one that most of you put for helper T cell. Okay, and then we have the two other components to make that other connection. And so the little red one there under E is the antigen, right? The APC. So this is kind of representing the full whatever the bacteria, virus, whatever it might be, right? Then it gets kind of processed and engulfed, and then a piece of it is expressed out here as the antigen. Okay, and the antigen is going to connect to the T cell receptor there, which is the blue thing coming off of the T cell. Okay, so we have those two connections, which are key here. And then 1, 2, 3 is just kind of the steps of the process of activation. Okay, so step number 1 is that helper T cell binds to the dendritic cell, right? Talked about those the two different connecting points, but that's just in general saying that the two cells are binding to each other. Okay, once those two connections are made, then we see the release of interleukins and cytokines, and specifically, it's IL-2 is interleukin 2. That's one of those cytokines. Cytokines are chemicals that the immune system uses to activate other cells, activate other immune cells, kind of stimulate the inflammatory process. Okay, and so that's what we're seeing here. So cells release cytokines to cause activation. Okay, and what does that activation mean? That activation means T cells proliferating and differentiating. Most importantly, for what we're talking about here, is some of them become cytotoxic T cells. Those are going to be the ones that do the work of the cell-mediated immunity. So number 3 there says T cells proliferate and differentiate, becoming cytotoxic T cells. And CD8 proteins are the characteristic proteins that come off of cytotoxic T cells. And so if you hear of a CD4 cell, that's a helper T cell. CD8 cell is the cytotoxic T cell. Questions on any of this or clarifications on anything? Okay, so now we have activated the adaptive immune system. I guess take one step back. Where is this happening in the body? Turn to each other on your team real quick and answer that question with each other. Where in the body is this happening? Okay, who's got the answer? Raise your hand. Who's confident and they know where this happens? Nobody's confident today? Anybody? Nobody? Does anybody know? December knows. Two guesses. Let's hear number one. In the immune system. That's a safe answer. Yeah. Okay. That's another very likely but not correct answer. You put yourself out there. I appreciate that. Thank you. Anybody else have another shot? Ashley? Lymphatic system. We're getting closer on lymphatic system. Okay. Where in the lymphatic system? Anybody? We're getting close. We can do this, I think. Yeah. What do we got, Rena? In the lymph node. This is happening in lymph nodes. This is what happens in lymph nodes. See, we got it. We eventually got it. Okay. What do we call B cells and T cells, as well as natural killer cells, a category of immune cells? Lymphocytes, right? Because they hang out in the lymphatic system. Okay. So the APCs don't hang out in the lymphatic system. They're all around the body looking for things. But when they get a hold of something, they make their way back to the lymphatic system, make their way to a lymph node so they can find a helper T cell and show that helper T cell what they found. Right? Kind of think of like your dog or your cat. When that cat, how many people have a cat at home? How many people's cat has brought a mouse into the house with its head ripped off or something like that to show it to you? How many people does that happen? Yeah, that's kind of how I think of the APCs, right? It's like, I caught something that's not supposed to be here. Here, aren't you proud of me? I'm usually not proud of my cat when I step on the dead mouse in the middle of the night, but it's kind of the same idea, right? The APC is bringing back this thing to show. Yeah, go ahead. Lymph noditis, yeah. Yeah, I mean, all of these functions would be potentially suppressed a bit, right? Yeah, I've heard of like lymphedema. I haven't necessarily heard of lymphitis. Is that something you've heard of? Or? Has it? Okay. Yeah, so it is common, like I was talking about before, like when you get any kind of infection, for the doctor to like feel up under your chin and behind they're feeling for your lymph nodes because your lymph nodes are swollen, which is very common with any infection. So I don't know if it was just generally that or if it's actually like a condition that the Mhm. Okay. Yeah, and yeah. So it probably just means the immune system is a bit overwhelmed with trying to deal with that infection, and so the lymph nodes get super swollen. It's normal to get a little bit swollen, but maybe if this was like an actual like diagnosis, then it might have been like extra swelling in the lymph nodes, which could impact drainage and could cause some general swelling in the body and things like that too. Yeah. It's probably that they're trying to fight the infection and they are fighting it and they're proliferating so much that you've got so many of them in there that it causes swelling, but then that could actually maybe limit flow of fluid through that space a bit too. So those are just some guesses. I haven't heard that specific condition, but yeah, great question. Yeah. Okay, so back to where we are. That was important. It's always important when you see something like this to think like, where is this, right? Like what is happening here? Like why are we even talking about this, right? That's a really important question to always ask yourself when you're studying too, right? It's like you could just get so caught up in the details of like what's on the page and really have no idea what you're even studying, right? It's the same thing with like locating these things in the body too, right? Okay. All right. So now that we've activated the immune system, the adaptive immune system, what do we actually do to fight this infection? All right. And so we're talking about the cytotoxic T cells here. What do? They have all kinds of things they can do. First of all, they migrate to wherever the infection is. Okay, this is called chemotaxis, right? So they're going to be called by other cytokines to come to the spot where the infection is. Okay, so they're going to migrate. They're going to release a chemical called perforin. Perforins are proteins that are all going to come together and poke a bunch of holes inside in the cell membrane of the cells that are infected by this, whatever this thing is. Okay. And now we got a bunch of holes in the membrane. And now that cytotoxic T cell is going to release another chemical called granzymes. And those granzymes are going to go through those holes that we just made, go into the nucleus of that cell and mess with the DNA in such a way where the cell destroys itself, commits apoptosis. Okay. And then it's going to release cytokines as well to call in more immune cells in that area. Okay. So that's pretty much what we've, the actions there. Let's go ahead and watch this little video that shows that. And you guys can kind of be filling in what's going on and labeling those things in the meantime as well. But let's see if I've still got it up here.
Inside all of us lurks a serial killer. Killer whose primary function is to kill and then kill again. These are cytotoxic T cells, a specialized member of our white blood cell. They patrol our bodies, identifying and destroying virally infected and cancer cells, and they do so with remarkable precision and efficiency. There are about 5 million T cells in a teaspoon of our blood, engaged in a ferocious and unrelenting battle to keep us healthy. These amorphous blobs move around quite rapidly, pushing out their leading edge and probing their environment as they go. When a cytotoxic T cell finds a cancer cell, membrane protrusions rapidly explore the surface of the cell, checking for the telltale signs of cancer. They kill their targets using poisonous proteins visible here in red. These cytotoxic granules move down special pathways in the cell called microtubules to the interface between the T cell and the cancer cell. The T cell punctures the surface of the cancer cell and delivers its deadly cytotoxins. This is very important in our bodies, where cells are packed together, as it focuses the lethal hit on the target and minimizes collateral damage to the neighboring healthy cells. The fate of the cancer cell is sealed. The T cell then moves on, hungry to find another victim.
All right. So dramatic and best with the British accent for sure. But pretty amazing too, right? This little cell is going around trying to find exactly what type of cell to target and then attacking it. Morgan, go ahead. Like the stuff that comes out of that cell could potentially infect other cells. Is that what you're saying? Yeah, yeah. So the idea would be that there's any part of that virus or whatever it might be that is infecting the cell, whether it's a virus or cancer or bacteria that's infected that cell. Anything that's then spilled out into the area is definitely less able to do its job, but there's other immune cells there too that can kind of attack those things as well. But the problem with having it inside of that cell is like rapidly either reproducing other cells that have the cancer or rapidly reproducing the virus for the cell, right? So it's kind of just trying to like cut that off to slow down the spread of the infection. Yeah, it's a great question though. Yeah. Okay, well, let's just walk through this one together here. So we've kind of got these labeled things here. So perforin is that protein release that is going to poke the holes in the cell, right? And then we can see that pore that's created there. That was under B, just a perforin pore. Okay, and then the next thing that's released to go through those pores, that's called those granzymes. Right? Those granzymes are going to go in, cause the cell to go through apoptosis. Okay, and so then the overall steps there, starting with number one, the cytotoxic T cell, or I just have the TC there for T cell, recognizes the antigen and then binds to the cell, right? Because that cell that's infected is also expressing that antigen, showing the immune system that I'm infected with this thing, right? So the T cell's looking for that. When it finds it, then it's going to release those two chemicals, release perforin and granzymes, all right? And then it's going to create those pores in the membrane. And then we go down to number 4. The granzymes then go through those pores, triggers apoptosis in the cell. And then step 5 on the bottom there is just going to be that it moves on to the next one. All right, so this is, go ahead, Ashley, yeah. Say that one more time. Is there any what? The T cells that are going around looking for stuff. Yeah, yeah, I don't know the exact answer to that. They probably have a certain kind of time frame that they survive, and a certain number of cells that they can destroy. That's kind of like with neutrophils can usually deal with around 20 bacteria before they die. Macrophages, it's around 100 bacteria. So it's probably might be something similar with these cytotoxic T cells. They kind of have a certain lifespan, and then they probably just die off. Yeah. But then there is kind of a suppression effect of those regulatory T cells that are released too, and they kind of help suppress the proliferation of new cells and things like that, and more of those become expressed once the threat of infection like decreases. And so there is like a regulatory part of this whole process that happens. So those cells might affect active T cells already too. So yeah. Yeah, no, definitely not. Yeah, because we have, like we were talking about last time, somewhere around 1 trillion unique antigens that our body's been exposed to. And so most of those are housed in the lymphatic system with memory T cells, right? And so then they're just kind of waiting there to be activated. And then once that group of memory cells does become activated, then we get a bunch of new cytotoxic T cells going around, probably live out their life. And then if the activation doesn't continue because the infection is contained, then we'd kind of just go back to that, just having the memory T cells for that one available. Yeah. Great questions. Other questions on this? Okay, all right, so that is the cell-mediated portion of the adaptive system. The other portion of the adaptive system is the humoral response, okay? And this is all about B cells, okay? So again, we're gonna have connecting points between that helper T cell. So the B cell is gonna bind to that activated helper T cell, okay? Now we're skipping the APC, right? The APC already did its job in activating that helper T cell. The helper T cell activated some T cells. Now it's going to go activate some B cells too. All right, so that helper T cell is going to release more cytokines, more interleukins to activate the B cells. They start proliferating. They start producing antibodies. And then when a B cell turns into, or when a B cell leaves the lymphatic system and goes into the blood and starts releasing antibodies, then it's called a plasma cell. Okay, so that's just what we call the activated form of a B cell. Okay, so it goes into the blood, starts releasing a bunch of antibodies, and it can release a lot. As you see, there are around 2,000 antibodies per second, and these antibodies can be active for somewhere around 4 to 5 days. Okay, so this is kind of walking us through the steps here. We can walk through this one together as well. So we've got our helper T cell again, right? That was already activated by that antigen presenting cell. Okay, it expresses a T cell receptor just like it did before. That is going to, and then it also has that helper T cell CD4 protein. Okay, now we've got a B cell with its MHC2 protein. Okay, and then we've got interleukins here being released. And finally, this is just the B cell in the process of becoming activated. It's showing its formation of antibodies. Those are going to be start to be released there pretty soon. Okay, so the steps here, step number one, that helper T cell binds with the self non-self complexes of the B cell, which is that MHC2. Okay. And that B cell has already encountered the antigen, and it's displaying that antigen on its surface. Okay, but it needs the T cell to activate it. And then finally, that T cell releases interleukins, that's going to then stimulate the B cell to do its job, to proliferate a bunch, make a bunch more B cells, and all those B cells are specifically making antibodies just for that one antigen there that was produced. All right. Questions on any of that? Still see some of you writing. I'll give you a sec to finish writing that down. Sorry, that was too much to write. I have to make a note to myself to decrease that next year. Okay. All right. About good? Okay, looks like most of you are done. So the question is, we make these antibodies, what do they do, right? How do the antibodies actually help us to fight infection? And there's kind of an easy acronym to use to help you remember that. It's typically just plan, but we can also add an O to it, which kind of gives us one more way that it works. So plano, we could say. So P stands for precipitation. Okay, this can be that the antibody binds to a bunch of small antigens that are soluble in water, so they're like dissolved in the water of our blood, clumps them all together, and then makes it so they kind of fall out of solution. So they kind of get stuck. They're not floating around the solution anymore. That's precipitation. Lysis is antibodies will bind to cells and then make it easier for that complement system we talked about before, which is all those proteins already in our blood that can help us destroy cells. The antibodies will kind of stimulate that process. Agglutination, we talked about with red blood cells when we have a transfusion reaction, right? Sticking a bunch of red blood cells together, that can happen to any type of cell, and it also leads to better chance of it being phagocytosed. And then neutralization. So antibodies can actually block active binding sites on something like a bacteria or a virus, so then that thing can't bind to the cell anymore like it's supposed to. Okay, and you can see that a lot of these make phagocytosis easier. And that's what opsonization is. Opsonization is kind of like marking something for phagocytosis. So marking it so then the macrophage knows to go get that thing specifically, right? And so that's kind of all of this together. Okay, so take a second and just label these things here and answer this question here on your clickers. All right, go ahead and send in your answer there on the clickers. So which one involves the complement system? You're not sure what the complement system is? Maybe somebody else in your team knows? All right, go ahead and send that in. All right, so about half of you are saying D, and we got about a quarter saying B, a quarter saying C. So we'll get to that one in a sec because it is D. But let's talk about A first. So A is looking like a larger type of pathogen, right? It's not a small one. And what these antibodies are doing is they're blocking the binding sites on that pathogen so that it can't bind to something in our bodies and cause problems. Okay. What about B? What did you think B was? The one we talked about with blood transfusions, right? So this would be agglutination, sticking a bunch of cells together. This is why that Y shape of those antibodies is useful because it has multiple binding sites, right? Can hold things together. C would be dealing with little tiny antigens that are dissolved in fluid. And when we stick a bunch of them together, they're then too heavy and too big to be dissolved in the fluid. So this precipitation kind of makes them fall out of solution, makes it so they can't move around the body anymore. Okay. And then lastly, the complement system here, this would be related to the lysis one, right? In the plan acronym. So remember, the complement system is similar to our blood clotting system, where we just have a bunch of proteins in our blood all the time, and we just have to activate one of those in the cascade, which activates another one, right? And then that causes blood clotting. Same thing with the complement system. We activate one of those proteins in the complement system, they eventually turn into these lethal little proteins that are just like the ones we just talked about that the cytotoxic T cells release that poke a bunch of holes in cells, right? And that's the complement system. So we poke a bunch of holes in cells, which eventually causes that cell to burst. Okay. All right. Questions on any of that? Okay. All right. So I've been talking about memory cells the whole time, but just a little bit more officially here. Both our T cells and B cells have memory cells. Okay. Again, remember, each T cell and B cell only responds to one specific antigen. So the first time we're exposed to that antigen, we don't have memory cells there ready to go. Okay, so we have to activate via the APC like we just talked about. Then the B cells and T cells proliferate. We get some cytotoxic T cells out of that. We get some B cells that are making antibodies. We don't have that many because we're kind of starting from scratch, right? But then we also get some memory cells that first time. Those memory cells are now just housed in the lymph nodes. And so then if that same virus or whatever it is comes back in again the second time, and then an APC finds it, goes and takes it to our lymph node, shows it to a helper T cell. Helper T cell releases chemicals to activate the immune system there. And there's a bunch of cells ready for that thing exactly, right? And so they're ready to go. They don't have to, we don't need to kind of completely recreate the wheel there. They're ready to go, right? And so, yeah, so they know kind of the weakness of the enemy is kind of one way to think about it, right? And so then that secondary response is going to be a much faster response, a much more powerful response. And most of the time, that makes us immune to something, right? That makes it so we're not going to get that thing if we already have that kind of weaponry and machinery ready to go. Okay, and this is just kind of showing that in picture form, right? Here's kind of our initial response to something. But then if we get that same thing again, we get a much larger response, many more antibodies released, many more cytotoxic T cells activated because we're already ready for it. We've got cells ready to do that. Okay, and this is the basis of vaccinations, right? And so vaccines have eradicated many diseases that were huge, huge problems, killing millions of people each year, right? Smallpox, polio, many other ones as well. Hepatitis vaccine. For nursing, you guys will have to get all kinds of vaccines. For any real clinical program, you'll have to get vaccines to be able to go into hospitals. And like I talked about before, that's either kind of a weak version of that pathogen or a completely inactivated version of that pathogen. And then that activates the immune system, right? That builds up immunity against that. And so then you're building up those memory B cells and T cells so that when you get the thing for real, your body's ready for that. And that first exposure then is pretty much treated like a second exposure, and you get a lot more powerful of a reaction to that. Okay. Questions on that at all? And some of you might be curious about the COVID vaccine was a unique one because it was a messenger RNA vaccine, which is different than these types, right? These types of vaccines are kind of some version of a virus if it's a viral one. But the idea with that is that causes that activates an APC, which activates a helper T cell. The whole thing we just went through. Messenger RNA vaccines are just kind of a new version of how to create vaccines, which are pretty much going to cause cells to reproduce that same antigen, which then gives us a more powerful response. It's kind of like taking a little bit of a shortcut in that process, and it was kind of a new thing. And so they're still kind of developing that technology a bit, but it was a different way to produce vaccines. So. Okay, so when we look at overall immunity in the body, we have 4 types. Okay, so when we're talking about antibody-mediated immunity, we're talking about creating antibodies with our immune system. Okay, there's one broad category called active immunity, the other broad category called passive immunity. Okay, so active immunity is that the body itself makes the antibodies. Passive immunity is you're not making them, but you're receiving them somehow. Okay, so we have 2 categories of active immunity. One is just the natural type, right? You were exposed to something, you've made antibodies against that, and now you have immunity. Okay, that's the first one, naturally acquired active immunity. Then we can also have artificially acquired active immunity, which is the vaccine, like we were just talking about, right? You weren't actually exposed to the virus, you were exposed to something, some version of it, some version that looked like it, or was a weakened version of it, and then you created immunity because of that. So those are both active forms of immunity. On the passive side, we have immunity through breast milk. Okay, so this is passive immunity, but naturally acquired. Okay, and this one's really pretty amazing because this is really the main way that formula can't replace breast milk, is because with formula we can get the nutrients and the nutrition pretty close to being what it would be with the breast milk, but the breast milk is also going to contain antibodies from the mom that the mom's immune system made to give to the baby, right? And so the example that I always love is the fact that babies commonly will take their hand and stick it in their mom's mouth when they're breastfeeding. It's just kind of a natural thing. A lot of times they'll like slap her in the face and like do all kinds of stuff, grab her nose and pull on her lips and stuff, you know. But there's some like scientists that have theorized that the baby is just exploring their environment, but also like obviously not consciously, but just kind of naturally, the baby's got stuff on its hands, or it's got bacteria, it's got viruses on its hands. And so by putting its hands in mom's mouth, it's giving mom whatever antigens are on that baby's skin, right? And now mom's immune system is going to make antibodies specifically for those things that are on the baby. And then they're going to show up in the breast milk pretty quickly, and baby's going to be immune to those exact things, right? So it's just a really amazing process that happens. And same thing when mom's sick too. Mom has a cold. She's already making antibodies against that virus, right? And they're in her breast milk, giving those to the baby right away, helping the baby fight that exact infection that the mom has, right? And so it's a very specific thing, but very like, it changes constantly, right? Whatever mom's exposed to, baby's going to get immunity towards that directly. And the very last type of immunity here will be passive immunity, artificially acquired. This would be the most common example is like a anti-venom type medication, right? Somebody gets bit by a rattlesnake or by an even more poisonous snake, have these certain chemicals floating around through their body. We can give actual anti-venoms that bind to those things very specifically and make it so it doesn't damage the person's body. So that would be passive immunity, artificially acquired. So, okay. Questions on any of that? Okay, so a couple immune pathologies. Okay, so hypersensitivities are forms of allergies. Okay, type 1 hypersensitivities are just what we think of as like our common allergies. Okay, some type of allergen enters the body, it gets picked up by one of those mast cells. Okay, this could be in any kinds of tissues, and those mast cells release histamine. We already talked about this. Histamine is a major vasodilator. Okay. So it causes relaxation of the smooth muscle in our blood vessels, but then in our bronchioles, in our respiratory tract, causes smooth muscle contraction. So it constricts our smooth muscle in our throat or in our lungs. Okay, opens up the smooth muscle in our blood vessels, vasodilation, and causes us to make mucus. How many people took something like a Claritin or a Zyrtec or an Allegro this morning? Yeah, we got a few, right? That's what it is. It's an antihistamine, right? Benadryl, same thing. All of those are antihistamines that are trying to block this action from happening. Okay, and a very extreme version of this is anaphylactic shock. Okay, with anaphylactic shock, somebody is very, very sensitive to a certain antigen or certain chemical of some sort. So it could be peanut allergy, could be dander from a cat, different things like that. And that allergen enters the bloodstream, and it simultaneously stimulates many, many mast cells all over the body. And so then there's a massive amount of histamine release, and we get way too much vasodilation in the blood vessels. And then we get way too much constriction in our lungs, right? And so it makes it really hard to breathe, and blood pressure plummets because we got the same amount of blood, but all the pipes just opened up, right? So there's not enough pressure to move blood around the body, right? And so this can be life-threatening, right? And the reason that an EpiPen is a treatment for this is because epinephrine, which is adrenaline, right? It does the exact opposite of those two things, right? The sympathetic immune system vasoconstricts our arteries, right? And it vasodilates our airways, which is the opposite of what histamine does, right? Histamine opens up blood vessels, constricts airways. Epinephrine does the opposite. It opens up airways and constricts blood vessels. Anybody have an allergy where they carry around an EpiPen? Yeah. What are you allergic to, December? Oh yeah, like bee sting, the wasp, but just specifically wasp? Wow, interesting. Okay. Anybody else? Yeah, Alyssa? Sure. How long does it take for Epi to work? Yeah, within like a minute typically, but I don't know, have you ever had to use yours, December? Yeah. Yeah. Is anybody else that raised their hand had to use theirs before? Yeah. Yeah, it's pretty intense, right? It's not something that you want to mess around with. It's not it's an intense drug for sure, but yeah, within minutes is what Andrew said. Yeah. Okay, a couple more things here. Another type of hypersensitivity is called a type 4 hypersensitivity. This is like when you get poison oak. Okay, so when you get poison oak, pretty much what happens is that stuff diffuses through your skin. It actually attaches to MHC1 complexes on your skin cells, and messes them up, and actually makes your skin cells look like they're foreign, like they're not supposed to be there. And so then the immune system comes around and takes those out, right? It says these aren't supposed to be there anymore, so it damages those skin cells, and this is the inflammation that you get, right? So the treatment for this would be any kind of cortisol-based drug, like cortisone cream, because that suppresses the immune system. Oops, that was not what I meant to do. I'm just writing immune suppression on the bottom. How many people have had poison oak before? It's rough. I grew up in the mountains and got it all the time as a kid. It's not fun. Poison ivy, same idea. I just wrote immune suppression on the bottom. Okay, let's finish up with the last two slides here. Yeah, so autoimmune disorders, we've talked about a bunch throughout the class already. Pretty much the immune system turns on your own body, right? And that foreign antigen is a lot of times it's when something comes into the body that has an antigen that looks very similar to one of our own antigens, but is not the exact same one. And so we make immunity against that, and then it actually works against our own body too. So lots of examples there. Leukemia is bone marrow disorder, bone marrow cancer, really, where it produces a bunch of immature lymphocytes that aren't ready to fight infection. So very high white blood cell counts with leukemia, but they're weak and they don't really do the job. And then finally, AIDS, caused by HIV. And HIV binds to that CD4 protein we were just talking about, among many other things, but it damages that CD4 protein and it knocks out our helper T cells, right? So we just saw the importance of those helper T cells. If those don't work, then we're in trouble, right? We can't activate our adaptive immunity at all. And so that's why it's called immunodeficiency virus. So, all right, guys, have a great rest of your day. We'll see you on Wednesday. All right, see ya.